Okay, thank you, Brian. Uh, I'm going to talk about something we did last summer. We conducted a field campaign, and so that's what I'm going to be involved in for the next few years is figuring out what this field campaign told us. This particular field campaign was called GOTHAAM. GOTHAAM stands for Greater New York Oxidant Trace Gas Halogen. Oh, you can read it. And it was a multi-collaborative interdisciplinary project, comprised of about 7 universities. A bunch of us here, Daniel and Paul, Steen were involved here. Um, let's see. The University of Colorado, Colorado State, University of California, Irvine, the University of Michigan, the University of Maryland, NASA, and the University of Washington. So we had a number of PIs involved in this campaign, and the goal of this campaign, here's some of the team. The goal of this campaign is to investigate the chemical processes that are occurring within the New York City region. The reason why we're interested in this is, well, there's a couple of reasons. One is that the New York City region, as you all know, is the most densely packed urban region in the continental United States, New York City and the surrounding area between Boston and Washington, D.C. So we have a huge anthropogenic industrial footprint, and this huge anthropogenic industrial footprint is responsible for emissions of a lot of stuff, both gases and aerosol, that then go on to react and impact air quality, and there are a lot of atmospheric chemical processes that occur which are associated with these types of emissions. But in addition to that urban footprint, which is huge, you actually have a big biogenic or biospheric footprint, particularly in the summertime. This is more seasonal, but for those of you, if you go a little bit north of New York City or a little bit west of New York City, there's a lot of trees, especially in the summertime, and a lot of deciduous trees, some conifers, some evergreens, but really this whole area surrounding New York City to the north and to the west is very densely populated with a lot of biota, right? Now, these biota, all of these plants and all of these bushes and stuff, they release a tremendous amount of gases. We've known this for many years. People have been studying this since the 1970s. And the type and the rate of these gas emissions depends upon the distinct area and speciation of what it is you're talking about. And so there's a number of questions as to what happens when you have this type of domain butted up against this type of domain. Because as you can see, if you've got one characteristic here and one characteristic here right next to each other, what happens when they mix? So when they mix, you may very well have processes that are dominated by this footprint or this footprint in the same region, depending on the meteorology. Those are the kinds of questions that we're interested in with GOTHAAM. In addition to this, we have to the south, the oceans, right? There have been a number of studies that show that marine emissions and marine chemistry is distinct, different compared to continental or terrestrial type processes. Just to give you an idea, in spite of the urban footprint and the magnitude of the population and all that stuff, the Northeast United States is an understudied region. This is what we told NSF. We said, look, we've got this huge footprint with biogenics compared to the majority of the rest of the continents of the United States, and yet there have been very few coordinated campaigns to address these issues. So just to give you an idea schematically of some of the specific chemical processes that we're involved in and that we're addressing, we had 4 objectives, and these 4 objectives are very, very broad. Admittedly, these 4 objectives really comprise probably 70% of the questions in the atmospheric chemistry research community. But we will address each parts of each one of these questions. You have 7 research groups, 8 research groups who will have primary pole position for looking at these data. And then within a year, it's released to the broader community where hopefully other people will use that. These objectives you can read, but basically we're looking at relative contributions from various VOC sources. Where do they come from? What happens to them in terms of their contribution to aerosol? Paul mentioned SOA, secondary organic aerosol. So a lot of the secondary organic aerosol actually is from biogenics and not industrial, right? So it's from tree emissions, isoprene, etc. Objective 3, quantify the relative importance of various oxidation processes for both mixed phase, so gas phase and aerosol species, and how the relative importance is going to change as you change that mixture of initial compounds, which is a function of meteorology. And then number 4, we wanted to look at the diurnal cycle, because we know that chemical processes occur at night, but those chemical processes are distinct from daytime processes. Daytime processes really are dependent upon the sun. When you remove the sun, other processes come into play. They're shorter, there may be less reactive processes, but nonetheless, they dominate once the sun goes down. So part of GOTHAAM, which was one of the more interesting parts actually, is to look at that diurnal cycle. How do things collapse in the evening, and how do things build up in the early morning? This just gives you a list of the instrumentation. What I just want to stress here is it was a comprehensive payload. This gives you an idea of what the aircraft looks like from the rear looking forward. So the pilots are past this bulkhead here. Here's a clock. And this is the instrumentation that we flew. We had about 27 instruments, a dozen different groups. You had about 12 people flying back here, 8 to 12 people flying back here on each flight, plus the flight crew in the front. We flew from early July to the end of August. I won't play this whole movie. We flew low and slow over New York City. This is the Hudson River corridor. You can see that it's quite polluted on this afternoon. It's around 5 o'clock in the afternoon. It's over Hudson River. So we saw a lot of different conditions. We flew in the early morning. We flew at night. So we did nighttime operations. This is flying down south the Hudson River corridor at 1,200 feet. We did that a bunch of times. Sunrise. Why is the sky so orange? What makes this so orange so early on? Those are the kinds of things we're interested in. This gives you an idea of the flight plans and the flight paths for all 21 research flights. So each research flight, each circle is about a 6 to 7 hour flight. We've had 21 research flights. So we used about 120 hours of aircraft time. And what's shown here is the time of day. So we started with daytime flights showing the blue, and then we started, then that went to evening flights in the yellow, nighttime flights in the black, and then early morning flights. We finished up with early morning flights end of August. It's already kind of getting cold because we had to push the campaign back. But anyway, those 21 flights, we 21 flights, and I get tired watching these flights just on this 30-second movie. So the fact that we actually did this, looking back, was kind of a Herculean task. I'm just going to spend a couple of minutes on showing some data. So one of the things that of course, we've got a crap ton of data that we're still going through the process of verifying and calibration, all that stuff. And our first science team meeting is this month. So there's a couple things I just want to show, which kind of was surprising to us. We knew this in real time. We knew this when we were flying. But one of the things that we saw just offshore, just to the south in the summertime during the day, were these highly stratified layers of pollution. So this is ozone. This is total aerosol load in micrograms per cubic meter. And if you notice, you see these just very, very distinct and very tight layers. These layers are very, very shallow, but they're extremely distinct. The chemical composition of each one of these aerosol layers, we will know. And this gives us information about the lifetime, its origin. But one big question is, you can see, this is within 1,000 meters or 3,000 feet. You're talking about 500 feet above the ocean, 700 feet above the ocean, 900 feet above the ocean. You have very, very distinct layers that are just hanging around and are stable over the ocean. And this is on a hot, sunny day. And yes, it's stable, but one might think that with the convection associated even over the water, this would be mixed. This would mix out. So this was a little bit surprising to us as an example. And we can actually use this to look at how these different layers are aged. Where did they come from? This layer might come from someplace different from this layer, for example, and this layer may come from somewhere different from this layer. Some may be biogenically dependent, some may be urban from 5 days prior. Again, this is like 20 to 30 miles offshore of New York City. All this stuff will blow back to New York City. So that was one of the interesting things that we're going to be teasing out. We're going to be focusing on. And another one, this is from Research Flight 8, to give you an idea. We actually had a lot of smoke in the area. It didn't descend so much down to the surface, but aloft, there were tremendous amounts of smoke, again, from Canada, from the Canadian wildfires. So on one flight, on one research flight, this was on August 4th, what this shows is you have, this is isoprene. You have a tremendous amount of biogenic trace gas emissions. These numbers, like 2 parts per billion isoprene, those are very, very high numbers. Those numbers are as high as what we see in Alabama, what we see in Atlanta. Pretty much, I've not seen higher numbers than this at altitude than what we saw during Gotham. So that was a surprise to some people because you just don't think about big biogenic emissions in the New York City region as being impactful, but they are. We see smoke during the same flights. We see no smoke during the same flights. So this is carbon monoxide. And then this is, what else are we looking for? Oh yeah, this is also a biomass burning tracer here. So what we can do is we can say, look, sometimes we see an increase in carbon monoxide. That increase in carbon monoxide, for example, is tied to smoke. Other times, that increase in carbon monoxide is not tied to smoke. So it's anthropogenic, it's urban. We can use these kinds of games to figure out what species and what mechanisms dominate the chemistry going on during the flight in that same region. So it's very heterogeneous, right? Down here, Zen was able to operate his LiDAR during the flights, which means he would show up sometimes 11:30 at night and work through the night. So thanks, Jen. And we've got these beautiful images from his LiDAR, which gives us a lot of information about the structure and the temporal development, evolution of the vertical structure of the atmosphere. So we can use this information to help figure out what the impact is of the dynamics and the changing mixed layer, all that stuff, as the diurnal cycle proceeds. We're going to use some of Zen's observations to help us figure out stability and all that other stuff, which is really important for chemistry. In chemistry, we really can't ignore the other branches of atmospheric sciences. Chemistry is the one branch where it's really, you need to know everything, right? So I think that's all I got.
For question or two.
John, it's so impressive. This project is so impressive. I actually have a question more about the why. Do you have a sense of why it was the case that the Northeast corridor has not been studied? Why was that a gap in the literature? Is it just reflective of NCAR is in Colorado, and so we do a lot of research out west in the wildfire areas? I'm shocked by that.
NCAR's in Colorado.
Yeah.
1. 2, it really just depends on the individual PIs, because this magnitude of project, and by the way, this is not totally comprehensive. I missed 1 or 2. Some of these are NSF, some of these are NASA, but really it just depends on the focus of the individual PIs. You can see that there's been a fair bit of work in the southeastern United States. There's been quite a bit of work, of course, in California, because California is a hotbed for air pollution, but the Northeast, I don't know. I don't know.
Programs that, I guess the thing of like University of Washington, Colorado State, so
UW does do something here. It's actually not on here. They did winter, which was in New York City. That's kind of like precursor to Gotham, and that was better than work.
Difficult place to fly too. So
just because everything.
I know
that's a good point.
We are experiment. We had the
it is
arm twist.
Yeah, that's a good point. I think it kind of scared off a lot of people.
when you
Yeah.
go out planning an experiment, you know, it's an order of magnitude more challenging in an urban area as opposed. to-
Yeah.
Yeah, that's
So
a good
exciting.
point.
Yeah.
I mean, you
Yeah,
know, it took the pilots a little bit of time to
Figure it
get
out.
used to the area. And
Yeah.
it wasn't that big of a deal.
Thanks, Tom.
I was just gonna ask a related question about how do you navigate the airspace in New York in a.
Carefully. Yeah. I mean, honestly, you know, so I've flown in this airspace for 15 years. So for me, it's like no big deal. But you got to remember that for anybody else coming into this airspace, there's a learning curve and they have to be willing to learn. One of the reasons why Roma, which was the year prior, didn't really get what they wanted to do in terms of fly where they wanted to fly in the New York airspace was because they weren't here long enough, right? That being said, I think some of it has to do with luck. You know, had we done it 2 years prior, it might have been a little bit trickier, but we actually got to fly exactly where we wanted to fly. And after about our 6th flight, you know, all the air traffic controllers knew who we were, like, hey, do whatever you want. So we did everything we wanted to do.
Buy 'em a beer and. Yeah, fun.
I have a couple questions. One is, how do you define smoke, no smoke? And then the second question, which you can answer, is within a strata offshore, do you have any criteria for aging the strata?
So I'll answer your last question first. Yes, so there's a number of ways we can age. Chemical aging is by ratio of species with different life forms, for example. So if you track use of sort of like a Lagrangian approach where you look at the change in that ratio, that gives you a chemical age. So there are multiple species we can use for a chemical age using a Lagrangian approach. If in this case it's not really a Lagrangian approach, you can still do that by using multiple tracers, right? So one gives you a base, and then the other one will give you a ratio, but then you have to assume what that initial ratio was based on the presence of other species. So I didn't mention this, but I've spoken with Hendrik. The way we do this is like very elementary. We look at this stuff and then we use a chemistry model with known kinetics, right? And known reactions. Well, if it's not in the model, you're not going to get it right, right? So what about all the stuff we don't know? And one of the things I'd like to do, I have to figure out how to do it because I don't want to spend all this time actually doing technical work. There has to be a way. I mean, while the data set's big, it's not that big. You know, it's maybe a few hundred kilobytes. You have all the data. There has to be a way to somehow, you know, take advantage of this and look at some of those, like almost like spectral imaging, but then go back, try to understand what the mechanisms may, you know, that may be responsible for any sort of relationship that you see. That's kind of a segue, but really, I think that one of the advantages of this data set, if we can look at it from a holistic and more integrated way, we might be able to tease out some things more simply and more straightforward using it. And what was your second question, Bob?
The smoke.
The smoke, great question. So the smoke, lots of tracers for smoke that are specific to smoke, pyrrole, for example, and others. So this, but this is a transport model. This was a prediction for the transport model.
Okay.
Yeah.
Great, well, thank you, John.
Yeah.
All the speakers here today, so.